All right, chapter 4, the mole, the concept of moles. Let's say that we're trying to order some donuts. So donuts are a frequent feature, as you hopefully probably know, of lots of grab-and-go breakfast settings. So like office meetings might have donuts at them, especially if they're in the morning. If you go to a seminar, if you go to a lecture or something at a college, it's entirely possible that somebody will bring donuts. If you go to church or you go to like small group meetings or something, especially if it's in the morning, right, there might be donuts there as well. Typically, your donut orders are going to be like 1 or 2 boxes, unless you're like really popping. You got a lot of people showing up. So you could just tell them however many donuts you want. Let's say though that you've got a large party in the morning and you want to bring donuts for everyone. So let's say grandma's turning 80 and she wants to have all her friends from the retirement home over and also all of your friends from the retirement home over. Why do you have friends at the retirement home? Anyway, questions for a different time. So you want to pick up 250 donuts from the bakery. If you show up to the bakery and you're like, I need to count every single donut, opening boxes, right? You'd be counting for quite a while. You're holding up traffic, all the people trying to get their orders of 250 donuts. It would take a long time. It'd be really slow. So what would be a lot faster is if you can just count the number of boxes. So if we look at this picture of lovely donuts, right, we've got 4 by 3, 4 across, 3 down. We've got a total of 12 donuts, a dozen, not a baker's dozen, but a dozen. So it would be much faster to count these 250 donuts just by counting the number of boxes and assuming that there's 12 donuts in each, and then maybe they'd have one that's got a couple short. So let's say that we're picking up this order of 250 donuts. That should be donuts, not 250 boxes. 250 donuts from the bakery. How many boxes of donuts should we expect to see in our order, roughly? We'd first need to know how many donuts fit in one box. So the question we're trying to answer is boxes of donuts. We've got 250 donuts. What's our conversion factor? How many donuts fit in one box? One box equals how many donuts? 12 donuts, a dozen donuts. So if we're picking up 250 donuts, how many boxes do we expect? Well, this one box equals 12 donuts is a conversion factor. We can have either one box over 12 donuts, or we can have 12 donuts divided by one box. Those are our 2 possible options for this as a conversion factor. We're starting with donuts, even though I accidentally wrote boxes. So 250 donuts. And we want to get to boxes. So we want this first conversion factor. 1 box over 12 donuts. So multiplying by 1 box, dividing by 12 donuts. Donuts cancel. And this should be 20 remainder 10. 20 point, what's the number? $250 divided by 12, 20.83 repeating boxes. Are they going to have part of a box, like just they chopped off the end of the box sitting up there on the counter? Probably not. That'd be really weird. The donuts would all slide out. So we would expect to see 21 boxes. So we'd expect to see 21 boxes sitting on the countertop. That's a lot faster, a lot easier to count out. They might even have them like in a nice little rectangle. We just count 3 or 7 across and then 3 up or 7 up, however many, right? Counting to 21 is a lot faster than counting to 250. And maybe they even have 22 boxes. They threw in a couple extras for us because sometimes places do that if you order a lot. So this is a more practical example, this is an analogy for Avogadro's number, for the mole. So a dozen is really convenient for donuts. But when we're talking about atoms, we've talked a little bit about how small atoms are. Like if you have your pinky finger and it's like a centimeter across, there's 18 million atoms that would fit just lined up end to end across your pinky finger, just to get across, right? That's not even like all the rest of the dimension of your pinky finger. So a dozen is not going to really help us out that much when we're talking about numbers that are so big. And so our version of a dozen is the mole. And we will often shorten this to mole, M-O-L. We're saving ourselves writing that one little letter. So M-O-L is usually what you'll see, but that means M-O-L-E, mole. This is a common theme of just like the smallest little time savers. So 1 mole is 6.022 times 10 to the 23. And that number is Avogadro's number. Sometimes you'll see this represented as capital N with a subscript of capital A, the N standing for number, the A standing for Avogadro. So sometimes you'll see that, named after Amedeo Avogadro. This is a number that we'll be using a bit in this class. There's a couple of ways that you can enter this into your calculator. When we get to a calculation, I'll show you that. Okay, so this is a similar process to converting between dozens or boxes of donuts and donuts, converting between moles and the number of the atoms. So 1 mole is equal to 6.022 times 10 to the 23 atoms. We can also swap out, instead of atoms, we could put formula units if we're talking about ionic compounds. We could also put molecules. You can put anything that you want there, just like we could put anything with the donuts. It doesn't have to be 12 donuts. It could be 12 nails. It could be 12 students. It could be $12. You can kind of put anything that you want in there. So we'll change the unit to fit our situation. But a lot of times it's going to be atoms, formula units, or molecules. So let's say that we want to convert 9.5 times 10 to the 25 atoms to moles. So we're doing atoms, just any old type of atom, to moles. We're going to use Avogadro's number to do that. 1 MOL equals 6.022 times 10 to the 23, in this case atoms. We can make either conversion factors out of that. So 1 mole over Avogadro's number, or Avogadro's number of atoms over 1 mole. You don't have to come up with both of them every single time. Hopefully, as we get more used to doing these conversions, you just pick the correct one the first time. But I just wanted to show us both of those options. Okay, so starting with 9.5 times 10 to the 25 atoms, we want to go from atoms to moles. We want to use this left conversion factor. That will get our atoms to cancel. So atoms cancel. We'll be left with units of moles, MOL. There's a couple of ways that you can put this into your calculator. One of the ways would be 9.5. Hit the times button. Should give you like this little asterisk, I think. Yeah. times, and then you might have a key for 10 raised to the power of something. So it might look like 10 raised to the power of 25. That key might be 10 with a little box on it. And it might show up with this little caret, or it'll be the 25 up there instead. Using that same strategy, we would hit our divide key, and then we need to use open parentheses. So start a set of parentheses, and we put in 6.022 with our little asterisk. 6.022 times 10 to the 23, optional close parentheses. This will get you the correct answer. There's another way of putting this into your calculator. 9.5, and then this small capital E, 25. And this small capital E comes from this key. It should have the dolphin noise on it. So we'll press the dolphin noise key. And this small capital E tells your calculator times 10 raised to the power of whatever comes after it. So it's the same as doing this times 10 raised to the power of, just compressed down. And then we would do the same thing, 6.022, use that little capital E, 23, and this will get you the correct answer. If you use this little dolphin noise key, you don't have to use parentheses because it links those numbers together in your calculator's brain. If you use the times, like in the upper example, you do need to use parentheses because it doesn't link those two things together the same way as if you use the dolphin noise key. Do people know I'm calling it the dolphin noise key? What sound do dolphins make? Right, something like that. That's why I call it the dolphin noise key. So those are both options. 9.5 E25 times, divided by 6.022 E23. This would be 157.75 ... I'm using that ... to show us there's other stuff that comes after that and we haven't forgotten about it. I just don't want to write it all out. And we would round this to two significant figures, 1.6 times 10 to the 2 moles. Do we have questions about the calculator part of that? Some calculators might also not work exactly the same way, so if this doesn't work for you, feel free to ask. I would also like to point out this is not the same as lowercase e. There's also a lowercase e. If you use the lowercase e instead of the small capital E, you will get the wrong answer. All right, the element carbon exists in two primary forms. Graphite, like in your pencil, and diamond, like possibly in a ring on your finger or earrings in your ears. How many moles of carbon, so we're looking for moles of carbon atoms, is 4.72 times 10 to the 24 atoms of carbon. So we're doing an Avogadro's number conversion, starting with atoms, carbon, going to moles, also of carbon. If we're going from atoms to moles, our Avogadro's number goes with atoms, and that's equal to 1 mole. It's like the 12 in a dozen. Since we're going from atoms to moles, we want the atoms part to be on the bottom. We want the moles part to be on top. So our conversion factor, 1 mole over 6.022 times 10 to the 23 atoms. So 4.72 times 10 to the 24 atoms, carbon. Put in our conversion factor, 1 mole over 6.022 times 10 to the 23 atoms. Atoms cancel. Carbon does not get canceled out, and we still have moles. So our units, moles, carbon. So 4.72, dolphin noise key, 24, divided by 6.022, dolphin noise key, 23, 7.84, after we round it for 3 significant figures, moles carbon. This is one of the big reasons that we learn scientific notation, dealing with these really large numbers of atoms. It's a lot more convenient to write out 4.72 times 10 to the 24 than it is to write out this. So we're saving ourselves a lot of writing. Questions about doing this conversion with Avogadro's number? Great. Let's say that we want to figure out how many atoms of hydrogen are in 2 water molecules. So this is doing a slightly different conversion. We're adding a step on. We've got a representation of 2 water molecules here. The red ones, these are oxygen, and the white ones, these are the hydrogens. Water has the formula H2O. Because of this 2, we know that there's 2 hydrogens in every H2O. 2 hydrogens in every H2O means that for 2 H2Os, we've got 4 hydrogen atoms. So our conversion factor is the 2 in the H2O. We could also do it for the oxygen, but it feels a little silly because there's only 1 oxygen. This works really nicely if we've got small numbers of things, especially if we have them drawn out in front of us. We can just count up all the hydrogens. But if we've got lots and lots and lots and lots of water molecules, like 1.5 moles of water molecules, and we want to turn that into number of hydrogen atoms, it becomes a little bit more complicated. So we're starting with 1.5 moles of H2O. We know that we can convert from moles to molecules using our Avogadro's number. So we take 1.5 moles H2O. We need to figure out how many molecules of H2O we have. So that's why we use our Avogadro's number. Each mole has 6.022 times 10 to the 23 molecules. And we get that's the wrong number. We get 9.033 times 10 to the 23 molecules. That's a lot of molecules of H2O. Each of those molecules of H2O has 2 hydrogens in it because of this subscript of 2. And that's why we do this 2 atoms of hydrogen for 1 molecule of H2O. So we double this whole thing, and that is not correct scientific notation. That's fun. I fixed it. 1.8066 times 10 to the 24, which we would round to 1.8 times 10 to the 24. We've got our atoms unit. We've got our chemical unit. Questions at all? The fun train keeps rolling. Okay, so molar mass is related to all of this, as you know. We used it a little bit yesterday. We've talked about it a little bit before. Molar mass is the mass of 1 mole. Just like a polar bear is a bear from the pole. I don't know why I thought of that, but maybe that's helpful. It's the same sort of like word construction. So molar mass is the mass of 1 mole of atoms of an element. It's numerically equivalent. It is the atomic mass in grams. So on the periodic table, using carbon as our example, carbon 6, 12.0108, depending on which periodic table you have. This 12.0108 is the average mass of a carbon atom if we're in units of AMU. So 1 carbon atom on average has a mass of 12.0108. This is sort of like what we were doing in our lab yesterday, where we were figuring out the average mass of 1 bean. If you average the mass of your 2 beans, you'll get some number. If you go and weigh each bean individually, every single one of those beans probably weighs a different amount than that average, but it represents the whole group of beans pretty well. It's sort of what we're doing with this 12.0108. So that's in atomic mass units, where 1 atomic mass unit is like roughly the mass of a proton or a neutron. It's also the same as the mass of 1 mole of carbon atoms with units of grams per mole. So typically we are going to use this grams per mole unit set rather than the AMU. So you might even just forget at some point that this is for AMUs, but it's also for grams per mole and AMUs. It's doing both of them. If we want to calculate a molar mass, it's kind of like calculating or counting up money. So if you go and rummage around through somebody's purse, presumably your own purse or somebody whose permission you've gotten explicitly to rummage around in their purse, and you find a bunch of money. Let's say we're 5 years old and we're rummaging through our mom's purse looking for money, and we just happen to pull out pieces of money. Right? You'll find some dollar bills, you'll probably find some coins, maybe even in a nice little pouch so they're not all over the place. You pull them out and you have to count up how many of each of the things you have to figure out how much your total amount of money is, right? Unless it's just dollar bills, which would be super easy. It's a little bit like that. So for molar mass, each of our elements has its own value. So we can think of those as like $1, a nickel, a quarter. Right? They've got their own value. And the periodic table tells us what those values are, which is convenient. So we'd multiply the number of atoms in the formula by its molar mass, and then add all of those up. So as an example, for this ionic compound with an oxyanion, sodium carbonate, Na2CO3. For Na2CO3, we've got, for sodium, 2 of them, 2 sodiums. For our carbon, we've got no subscript, so it's just 1 carbon. For our oxygen, we've got 3 of them. So we multiply the number of atoms that we have by the molar mass that we got off the periodic table. That'll give us a total of the molar mass for that element. We add all of those up and we'll get the total. If you don't want to do them individually, where you do the 2 times 22.990 to get 45.980, and then you do the next one, and then you do the next one, you can enter all of these all at once. And you don't actually need any parentheses either, which is convenient. So you can do 2 times 22.990 plus 12.011, because it's times 1, so we just ignore it, plus 3 times 15.999. Press the Enter key, and you should get 105.99, or 988. A similar related compound is calcium nitrate, CaNO3,2. This is a component in fertilizer. Determine the molar mass of calcium nitrate. So we've got CaNO3,2. We want the molar mass of that whole thing. So we're going to start off by figuring out how many of each of the elements do we have. Calcium is up front. It's by itself. It doesn't have any parentheses around it. It doesn't have any subscripts. We only have 1 calcium. Looking at our next element, nitrogen. Nitrogen doesn't have a subscript, but it's in parentheses, and there's a 2. So we have 2 nitrogens. Oxygen has a 3 subscript on it, and it's in parentheses with a 2. And so it's going to be 2 times 3 oxygens. So for oxygen, we have 2 times 3, 6 oxygens. Then we would go to our periodic table. We find the molar masses. 40.078 looks like for calcium. Nitrogen 14.070067. I'm just going to pull out my yellow sheet instead of looking across the classroom, the tiny little numbers on the wall. Let's take a moment to appreciate that I teach this class. I've taught this class at least 10 times. I don't have the periodic table memorized. It's a waste of time. It's my professional opinion. All right, 14.067. I was reading it correctly. And for oxygen, I like to use 15.999. So we're going to multiply these. And then add them up. Or do a sum. So 40.078 plus 2 times 14.0067 plus 6 times 15.999 equals, you should get a number of something like 164.0854. And I've done something awful. I've done something horrible. What have I done? On this slide, not in my life. I'm a perfect angel outside of class. What did I do or not do on this slide? There's no units. A terrible, terrible cardinal sin. No units. We need units. Our units, grams per mole. All of these need units. That's the terrible, terrible, awful thing that I forgot to do. Or that I did, because it would have been a good thing to do it. 4 molar masses, don't bother with the significant figures. Just don't worry about it. It's not that big of a deal. As long as you're using at least the numbers on your yellow sheet, or like this periodic table in our class, you should have enough decimal places that significant figures will not be limited by your molar mass. If you instead were to use like 16, 14, and 40, that is not enough decimal places. You need to have a couple of decimal places. We want to make sure that we're not limited for significant figures by our molar masses. The one instance where it would be fine, good or okay to use 16, 14, 40 for those molar masses is if you just want a real quick estimate of an amount. I'll do that sometimes. Not in the class probably, but I do that sometimes. You just want a real ballpark estimate, then that's fine. In this class though, generally not going to really be using ballpark estimates like that. Questions about the molar mass stuff? All right, if we want to do conversions between moles and mass, this is where we use molar mass. The molar mass is the mass of 1 mole. Molar mass has units of grams over moles. That means that it can be used to convert between those two units. That's a common theme. Anytime that you've got 2 units in something, like density has grams over milliliters or grams over cubic centimeters, you can convert between those 2 units. So we want to convert between moles and mass. We use molar mass. You can go either way, you can go both ways. Let's say we've got 3 moles of forbidden marshmallows, calcium carbonate pellets. What is that mass? The mass of 3 moles. So we are finding mass of 3 moles of calcium carbonate, CaCO3. And for this problem, we're even helpfully given the molar mass. We're starting with 3.00 mol CaCO3. We want to convert this into grams CaCO3. The 100.09 grams goes with the moles part. So we could also write this 100.09 grams over 1 mole. Those are identical. Those are equivalent. Fortunately for us, we have moles. Moles is in the bottom of our molar mass, so we multiply. So the 100.09 grams and the 1 mole go on the bottom. You can also include the CaCO3 as part of your units. I usually leave this part off from the conversion factor because we've got one on the top, we've got one on the bottom, those would cancel out. However, if we're using multiple molar masses, maybe this would be a nice way of making sure that we're using the correct one. Okay, so moles, CACO 3 goes away, so 3 times 100.09 equals 300.27 grams. Round to 3 significant figures and put it in scientific notation. 3.00 times 10 to the 2 grams CaCO3. Questions? As a general rule, you're expected to be able to come up with the molar mass for a chemical compound. I will occasionally be nice on exams and give you the molar mass just to save your brain power, since there are 50 questions. But like this, what's the mass of 3.00 moles of calcium carbonate? That by itself is a question on an exam. So we would have to figure out, search our brain for nomenclature. What's calcium carbonate? Figure out the formula is CaCO3, calculate out a molar mass of 100.09 grams per mole, and then multiply it by 3. So that could be something that shows up on an exam. You would be able to do all of those parts. We're expected to be able to do all those parts. Chromium metal is used for decorative electroplating of car bumpers and other surfaces. Find the mass of 0.560 moles of chromium. What is our symbol for chromium? Cr. Chromium is Cr. We're finding the mass of 0.560 moles of Cr. So we're going from moles to mass. Grams is a common unit for mass. Can we do this in one step? If you're blind guessing, you've got a 50-50. Can we do this in one step? I'm seeing some nodding. The answer is yes, we can do it in one step. What are we going to use to convert between moles and mass, or moles and grams? What do we call it? Say it with me. Molar mass. Cool, nobody said it with me, but that's fine too. I'm not sad. The molar mass for chromium is what? On our yellow sheet, it's 52.00 grams per mole. So starting with 0.560 MOL, capital C, lowercase r, 0.560 moles of chromium. We're going to multiply by 52.00 grams per mole. Since it's grams per mole, the moles goes to the bottom. So moles cancel. So we've set this up correctly. And we would be left with units of grams CR. So 0.56 times 52. Calculator says 29.12 grams chromium. Round that down to 29.1 grams chromium. Let's say we want to add another step onto that, because of course we do. a certain reaction produces 2.81 grams of copper 2 hydroxide CuOH2. Determine the number of moles produced in the reaction. So it produces 2.81 grams. We're told what the formula is. We want to determine the number of moles. So we're going from grams to moles, and our chemical is copper 2 hydroxide. Can we do this in one step? Survey says yes, we can do it in one step. What are we going to use to convert between grams and moles? Molar mass. Do we know what the molar mass is for copper 2 hydroxide, CuOH2? Not yet, right? We need to calculate it. We've got 1 copper, 2 oxygens, 2 hydrogens. 2 oxygens and 2 hydrogens because of the 2 outside of the parentheses and only having 1 oxygen, 1 hydrogen in the parentheses. Copper, 63.55 grams per mole. Oxygen, 15.999 grams per mole. Hydrogen, 1.008 grams per mole. So we multiply 1 by 63.55, add to that 2 times 15.999, plus 2 times 1.008. You get 97.564 grams per mole. How many significant figures? It's a trick question. We don't care. Enough is the answer. It's enough significant figures. Okay, so 2.81 grams copper 2 hydroxide. And then we use our molar mass, and we get moles copper 2 hydroxide. We'll round it for 3 significant figures, 274 moles copper 2 hydroxide. Questions? If your grandma, who's 90 years old, said, "I just bought a Harley, any questions?" and you don't have questions, I'd be a little concerned. Maybe grandma's really fit. There should be questions here. This is not the correct answer. Why is this not the correct answer? What's missing? Where did I go wrong? Units. I did not include units. I also ran out of space because that's just classic. That's just absolutely classic me. What unit goes with the 97.564? Grams. And the moles would go on the bottom. So because I didn't write out my units, hopefully some of you saw it anyway. Hopefully some of you saw why it was wrong anyway. because I didn't write out the units, and we didn't check that the units canceled out, the units we'd actually be getting out here are grams times grams, so grams squared per mole. And those are crazy people units, as it turns out. So this is not the correct way to set up the problem. We didn't get our grams to cancel. We want the grams to cancel, so this 97.564 with the grams needs to be on the bottom, the moles needs to be on the top. Got to flip our conversion factor. So instead of multiplying by molar mass, we want to divide by molar mass. So 2.81 grams copper to hydroxide. Flip our conversion factor because things did not work out. And now look at that, grams on the bottom, grams on the top. Those will cancel, beautiful. So we're dividing instead. So 2.81 divided by that 97.564. And we get 0.0288 moles copper to hydroxide, CuOH2. And that is the correct answer. Now, do we have any questions? Trying to demonstrate if we write out our units, we can catch our mistakes. Or if we write out our units, we can look back. If we write out our calculations, we can look back at it later and figure out why we got something wrong. Like on an exam, for example. If you write out your calculations, you can look back at it later and know what you were thinking and why things might have been wrong. Okay, we're going to link these. Going to combine these conversions. So we've learned how to convert between particles, atoms, molecules, or formula units, a smallest piece of a chemical, and moles with Avogadro's number. And we've also learned to convert between moles and mass with molar mass. So we can stick those two things together to convert from the number of particles, atoms, or molecules, or formula units, and we can convert that all the way to mass in grams, or whatever other mass unit we might want to use. Let's do one example. How many molecules are in 20.0 grams of chlorine gas, which is Cl2? We want to start with grams, Cl2. We're finding molecules, also of Cl2. Can we do that in one step? Can we go from grams to molecules in one fell swoop? No, we cannot. We need a couple of steps. What can we convert to from grams? Can we convert to sandwiches? Can we convert to pieces of spaghetti? Can we convert to moles? We sure can convert to moles, so we'll go to moles. Can we convert from moles to molecules in one step? Survey says yes. For these, we're going to use molar mass and the number of the Avogadro's number. So 20.0 grams Cl2. We're going to use our molar mass for Cl2. For Cl2, the mass is 35.45 grams per mole for each of them. So it's going to be 70.90 grams per mole. for this first step, the 70.90 is going to be used. Are we multiplying or dividing by 70.90? Does the grams go on the top or the bottom? The bottom. So we're going to divide by our molar mass. 70.90 grams, and the moles part goes on top. This gets our grams to cancel. So I'm drawing a line through it just so that we know where we're at, making sure that our units cancel so that we're not setting ourselves up for failure. And then we're going to use Avogadro's number, which is 6.022 times 10 to the 23. In this case, it's going to be molecules, and that's equal to 1 mole. We need the molecules part to go on top and the moles part to go on the bottom. So we're multiplying by Avogadro's number. The moles cancel. So our units that we get at the end will be molecules of chlorine gas Cl2. So 20 divided by, since it's on the bottom, 70.90 times 6.022 times 10 to the 23, 1.70 times 10 to the 23 molecules Cl2. This is after rounding for 3 significant figures. There's a good chance that what your calculator said looks something like this. So your calculator will often use this E as a way of saying times 10 to the 23. So this E23 means times 10 raised to the 23rd power. Alternatively, it might just have at the end a small 23 that's up in the top right corner. Something like that. That also means the number, the regular size number, the 1.698 all the way out to this last 6, times 10 to the 23rd. Questions about any of that? Okay, then we will pick up on percent composition next class.